Okay, this is our Mars rover helicopter project. Okay, so we were given this project about a helicopter for the next Mars rover, and basically we're given the acceleration function here, and we know a few additional things like it starts from rest, and we know the horizontal distance away, and so yeah, we really want to find uh, the motion of the helicopter and how much it spends in the air and where the helicopter lands. So I'm going to try to describe the motion to you. So in order to understand the motion of the helicopter, we're going to need to do a couple things to this acceleration function. The first is to understand what the velocity is going to look like, we're going to need to integrate the acceleration function, and then we're going to integrate that velocity function to find a position function. And that'll help us understand its movement. So the professor went ahead and did all that for us, and we got this position function, and we also know a couple additional things. We know that the overall change in x is a constant of, which is just the distance that the helicopter travels. We know time, the equation for time, and we know an equation for delta y. So let's go ahead and graph a few of these things and see if we can understand what this helicopter is actually doing. So this is the position in the x direction. I made a green line for where the helicopter starts and a blue line for where the helicopter ends. And this is x direction over time. So the helicopter is going to start on that green line, and it's going to constantly be moving to the right, not at constant speed, but it's going to be going a little slow, speed up for a constant amount in that middle part, it looks like, and then it's going to slow down to a stop when it lands at that blue line. Okay, so now this is the position in the y direction over time, and it's a little different. We can see that it starts below 0 and it'll end above 0. So what we really gathered from this is that the helicopter is kind of starting in a crater and maybe landing on top of a rock. It gains elevation over time in terms of position in the y direction. Okay, so the next thing we can sort of try and understand is the velocity in the x direction over time. And it's the same sort of thing. It starts at the red line, ends at the purple line on the right. And so this is the x direction. The velocity is going to start at 0 when the helicopter is at rest, and then increase until the middle of the flight, which is where x equals 0, and then it'll start decreasing on that second half of the flight until it lands at rest again on the purple line. Okay, so now we can look at the velocity in the y direction over time. It's a little different, a little bit more complex. Again, it starts at rest on that red line, and it's going to have positive velocity for a short interval in the y direction as it's elevating, and for that first little bit. And then we can see in the middle, when our velocity is 0, that means the helicopter is not moving up at all, and that's kind of when it's staying at that constant altitude that we saw on the position graph, and then towards the end it needs to climb a little bit higher again, so it has a positive velocity again until it gets to that purple line when it comes down for the landing, and it'll have 0 velocity once again. So the last thing we can kind of try and look at to understand the motion is the acceleration. This is the acceleration in the x direction over time, and we can see it looks pretty simple. It's a linear graph. The acceleration starts positive at the left side when the helicopter takes off, and then it's decreasing the whole way through at a constant rate, it looks like, and yeah, in the middle of the flight it gets to 0, and then it'll start decreasing, or going into negative velocity rather, until it lands. So yeah, you can see that it's increasing it's got a positive acceleration, which means it's increasing in velocity until the middle of the flight, where it's got a negative acceleration and decreasing in velocity, which we saw in that velocity graph. Okay, and then finally, acceleration in the y direction. It's definitely more complex. We can see that it starts increasing, or starts decreasing rather, but with a positive acceleration, and then it crosses that x-axis and becomes negative for a short period of time. And so yeah, that means that helicopter on the way up, it's increasing in speed as it's trying to climb, and then it kind of needs to slow down again as it reaches back to that constant part in the middle where it's not increasing in speed at all. That acceleration is going to equal 0. And then for the next climb, you do the same kind of thing. It needs to increase in velocity, which means positive acceleration, and then slow down again at the end for the landing, which is that negative portion of the acceleration. So that's kind of how we can understand the motion of this helicopter using those equations and some graphs that I put together.
Because this